Hello everyone, and today in this video we will discuss and demonstrate the HUCKEL molecular orbitals. We will visualize it using the WebMO search engine, okay, for about 3 molecules in this particular video. Okay, let us understand the concept of HUCKEL molecular orbital a little. Okay, so this is the person Eric HUCKEL who is behind this theory. You can see his picture over here. And what this method actually does. Okay, this is shortly called HUCKEL method. It was developed in 1930, which paved way to the semi-empirical calculations which we discussed in the day 1 video for the Hamiltonians, right? So Mopak Hamiltonians, yeah. So it is very simple and it is based on the linear combination of atomic orbitals, molecular orbital method, which is shortly known as LCAO-MO method. Okay, so what can be determined using these molecular orbitals? Yes, you can determine the energies of the molecular orbital of the pi electrons in the pi delocalized molecules. Yes, so HUCKEL worked on the pi delocalized molecules. So what all molecules, some large molecules which had the pi bonds, they were studied properly. Their energies were determined using this molecular orbital method. Some examples include the ethylene, benzene, butadiene and your pyridine. So like that you have the examples. These are some planar molecules. Okay, and you can, here in this video we will be visualizing the HUCKEL molecular orbitals for these 3 molecules, ethylene, benzene and butadiene. And also you can see this conjugated system, this model is acting is used for the particle in one-dimensional box. So this acts as a model to explain the conjugated system for particle in one-dimensional box, and it is a better model for conjugated systems. So far for conjugated system it was a question mark, but after HUCKEL developed this theory, it was very easy to understand the conjugated systems properly. Okay, yeah. So then why we need this HUCKEL molecular orbital theory? Okay, the first point you should notice is that it is the first MO theory that could be applied to large molecules. Okay, so far you have learned in your lower classes, like you will be learning about the oxygen molecule, the nitrogen molecule, their molecular orbitals and everything. But when it goes to larger molecules, the HUCKEL molecular orbital theory finds a very good application there. Okay, and the second point, you can see a theory that can be implemented without the aid of a computer. Yeah, so you don't need a computer, you can just do certain approximations and you can work out with it. But to visualize the molecular orbitals, okay, you need a computer so that you can see the 3D arrangements and everything. You can draw in your paper the orbitals, but one such thing is that you can visualize it in a proper way, in a 3D way. Okay, that's one of the advantage if you use a computer. But normally the calculations can be done with your pen and paper, no need of a computer, because those calculations are very simple by solving certain determinants and everything. Okay, and see, it has been starting point for very successful theoretical interpretation of the UV spectrum. Yeah, you understood, no, that CNDO method which we discussed in day 1, right? So the CNDO method uses the UV visible spectrum was answered. So HUCKEL theory was the start for this one. Okay, so it has been the starting point for more advanced theories. Yeah, we know that for developing all the NDDO models and Zindo, Indo models and all the Hamiltonian concepts, the semi-empirical models came from this HUCKEL molecular orbital theory only. He is the start. This theory is the start for all the semi-empirical calculation models. Yeah, see, why you call this HUCKEL molecular orbital theory under the semi-empirical theory is that you can see that it is very approximate, because HUCKEL introduced lot of approximations. You can just Google out or search lectures. You can find that the HUCKEL molecular orbital theory made many approximations. They considered the overlap integrals, they just left it at 0, like that. He made lot of approximations. One such approximation is that he neglected the electron-electron repulsion concept. So what happened? So the electron-electron repulsion energy concept was neglected, and hence you call the HUCKEL theory as a semi-empirical theory. This is all about how HUCKEL came under the semi-empirical concept, because it included a lot of approximations. Okay, then comes your extended HUCKEL theory. What this extended HUCKEL theory actually mean? It is shortly abbreviated as EHT. Okay, this theory extends to atoms beyond carbon to three-dimensional molecules. So from carbon atom to three-dimensional molecules, so 3D molecules. So you can work out this with that. So this is your extended HUCKEL theory. Okay, it describes your sigma bond, pi bond, and even the delta bonding. Yes, so using your WebMO, you are going to visualize the extended HUCKEL theory. You will be visualizing the 3D arrangements, not only the pi orbital. Normally that HUCKEL orbital, it included the pi electron arrangements in the molecular orbital, but in the extended HUCKEL theory, it will include all, not only the pi bond, not only the delocalization electrons, it includes all your sigma electrons, your pi electrons, and also your delta electrons. That is all the sigma, pi, and delta bonding electrons. Okay, all their molecular orbitals can be visualized in your WebMO, which is based on the extended HUCKEL theory concept. Okay, so see, the EHT contains essential elements of molecular orbital theory at very minimalistic level. So although it will not give very accurate results, but it is moreover reliable. Okay, and it requires very low computational demand and very little time consuming. It's very easy to analyze. And one thing you have to notice is that your WebMO includes only the extended HUCKEL theory. So all the sigma, pi, and delta bonding molecular orbitals will be shown. Okay, so don't get confused with that, why only pi electrons should be filled and why the sigma orbitals are showing and it's not compared with this. Normal HUCKEL theory, you see, it shows only the pi electronic arrangements in your molecular orbital. But the extended HUCKEL theory includes all the valence electrons and your sigma, pi, and delta bonding electrons also. So that's why we will get all the orbitals as a whole. Suppose if in your molecule, if you have around 11 bonds, for each bond it is 2 electrons, right? So you get 22 electrons. So totally what happens, for 22 electron occupancy, 11 molecular orbitals will be shown. The 11 HOMO and 11 LUMOs will be shown. So like that. So don't get confused with that. So we will go with some demonstrations. Okay. Yeah, so we have many applications of this molecular orbital theory to conjugated molecules. One such example which I include is that the ethylene molecule. Okay, I go with the ethylene molecule. You can see in ethylene you have only one pi bond. Yes, you have one pi bond, and you see it contains for 1, 2, 3, 4, 5. So it involves totally how much electrons? 10 electrons over here with sigma. When pi comes into picture, it becomes 12 electrons. So totally 12 electron is there. So the sigma bonding framework is 10. When pi bonding framework comes, it is 12. Yes. So this is the HUCKEL molecular orbital. See, totally we have only one pi bond here in your ethylene molecule. So see, in this HUCKEL molecular orbital normal, this is not the extended, this is a normal HUCKEL molecular orbital theory. You see only the pi electron is filled, the 2 electrons. It will be like this with 0 nodes. But when you go to the LUMO, the next level, you see no electron because only 2 pi electron, it is filled in the HOMO itself, and LUMO is empty, and you see it's the next level, and you see you have one node. Okay, and this can be visualized in the demonstration. Okay, now let's go with the demonstration of the ethylene molecule using your WebMO. So you go to your WebMO job manager by logging into your WebMO, click new job and click create new job. Yes, I have my page for building the molecule. Click build and you select carbon. I'm going to draw ethylene molecule now, so click and drag for other carbon and drag along the bond so you make a double bond. Okay, now we have to add hydrogen. Click clean up and add hydrogens. Yeah, it's added, and now you have to optimize it, right? So I just go to clean up and gives mechanics optimize. Yeah, it's optimized now, and also you can give the comprehensive mechanics, what all possible you can give it, and yeah, it's symmetrized now already, so no problem with that. And now I click calculate and go to HUCKEL and select molecular orbitals, and see I can get the orbitals for the HUCKEL molecular orbital for that molecule, right? And you see when I click that 6 is your HOMO and the 7 is your LUMO, so it is arranged in a different manner, so don't get confused with that. See how the HOMO of the ethylene is shown clearly as we saw in the MO picture. okay, which I showed in the slide, right? That is your HOMO with 2 electron occupancy, and this is your LUMO. See, as I showed in that picture, it is like that with 1 node, right? So HOMO, your LUMO. So HOMO is with 2 electron and LUMO is with 0 electrons. So now let me show you for the 2 pi electron system, that is your 1,3 butadiene. Here you find it contains 2 pi bonds, right? So we have totally 4 pi electrons, but when you include all the sigma electrons and everything, it comes under the extended HUCKEL theory, and so you get a lot of molecular orbitals for all your sigma and pi also, okay? So we have to identify it properly in that. Okay, so you see that this is your molecular orbital diagram for butadiene. Only the pi framework is shown here. See, at starting no node, then you have 1 node, then 2 nodes, and you have 3 nodes. See, this can be seen properly in this one. See here, there are 2 pi bonds, so for each pi bond 2 electrons, totally 4 electrons, so 2 and 2 is filled here. Here you see 0 nodes. Here you can see 1 node, here you have 2 nodes, here you have 3 nodes. All these can be visualized in the WebMO software, WebMO search engine, okay? So we will demonstrate for 1,3 butadiene molecule now, okay? So let's go with our butadiene molecule. So I have the page here. I just construct the butadiene molecule here, build, click carbon, then click and drag, click and drag, click and drag. So for 4 carbons for but, and then you just make the diene by tracing along the bonds, okay? So you get the diene now. Click clean up and add hydrogens. Yeah, your hydrogens are added now, and you need to optimize. Go to clean up, click mechanics, optimize, and yeah, it is optimized to proper geometry, and you have to symmetrize it, right? So just click on that symmetrize icon and see it is symmetrized properly, okay? Then you can give comprehensive mechanics too for a further thing, and give calculate, click HUCKEL and select molecular orbital, the same procedure, and you see you get your molecular orbitals, and you can just click and select. So totally 11 bonds, so 22 electrons are there for us with 11 homos, and see the 9th orbital is your pi 1, okay? See here the pi 1 which is shown here. For that pi 1 electron, we have 2 pi bonds, no? So in that the first pi bond with 2 electrons is in this picture, the MO number 9. See the HOMO number 11, see, that is the 2nd pi orbital. The 10th one is your sigma, so leave it. Now see the pi framework, and you see the HOMO shown here with the 2 electrons here, right? So the 9th one is your pi 1 bond electrons, and your HOMO 11 is your pi 2 bond electrons. Yes, and see the pi 3 and pi 4, the LUMOs, okay? So you can see it here, right? The same thing is displayed there, right? This is the LUMO, that's why the color is different. HOMO, it will be colored with red and blue. LUMO is colored in green and yellow. See, the 13th LUMO is empty, so it is showing in this color, okay? This is how you do with your 1,3 butadiene. So now we will move on with our 3 pi electron system. We are increasing the pi electrons now. For 6 pi electron system, that is your benzene system, which has the delocalized pi electrons. So we will visualize that HUCKEL molecular orbital over here, the extended HUCKEL molecular orbitals. Yeah, you can see this is your benzene molecule with 6 pi electrons. So according to Frost circle theory, you know that you can inscribe your benzene into that a circle, inscribe it in a circle, and you can find the molecular orbitals will be like this: 1, 2, 3, 4, 5 and 6. Okay, so you have like that, and you just label them with the wave function symbols, and then you go with the electrons. So totally 6 pi electrons. I fill all the 6 pi electrons over here, and you can see how it is there, right? 0 node and 1 node and 2 nodes, and like that it will be going on. Okay, there also this is the 3D picture of your HUCKEL molecular orbitals for your benzene molecule, and we will visualize this using your WebMO now. Okay, the same pictures can be visualized there. Okay, so we will start with constructing our benzene molecule now and visualize the orbitals. Click build. Here I just go with the fragments. Okay, I just click rings and you select the benzene, click OK and click on the screen. Okay, left click on the screen, you get the benzene molecule. Give clean up, mechanics optimize. Yeah, it's optimized to proper geometry, and you symmetrize using the symmetrize icon. Yeah, the D6H point group, it is properly symmetrized now. So now what you have to do, click calculate, click HUCKEL, click molecular orbitals, and you see the orbitals that are there. Okay, we have 30 electrons here, so you can visualize it properly. See, when as I click, you can see all the orbitals shown, right? Yeah, see, the 10th HOMO is the pi 1 system, correct? See, the pi 1 which is shown here is this 10th HOMO. Okay, yeah. See, the 11th one you have here, how it's showing, your 12th one, see, 13, your 14, your 15th HOMO. You can see it. Okay, you can get more details with that. And see the LUMO which is picturized here. Okay, your LUMO which is here, that pi 4. Okay, if it involves in delocalization, electron goes there, and you can see the LUMO. The color is green and yellow, which indicates it's LUMO. Okay, this is how you do with your benzene. So very easily you can do with